Alright, second half of 5.3 was solving trig equations, and we're picking up with example 7. Alright, on example 7, when we first start, we might get a little stuck, because we look at this one, and if we tried to, substitute it out, which we do sometimes, we would have, like, x plus 1 is equal to y. I don't know what to do with that. Like, I don't know how to solve that. We saw the very last one that we did yesterday when we finished up. We had a problem that had sine and cosine in it, and the way that we resolved it was we replaced either the sine with cosine or the cosine with sine. But the only way to do that is if I have a square, because then I could use that Pythagorean identity, right? And so that's why today they give us a suggestion of another way that I might utilize to solve these. And that is that I could square both sides. If I go through and I square both sides of this inequality, then I've got cosine x plus 1 squared is equal to sine x squared. Now, cosine x plus 1 squared literally means cosine x plus 1 times cosine x plus 1. So if I FOIL that out, that would be cosine times cosine is cosine squared. Cosine times 1 is cosine. 1 times cosine is cosine. And 1 times 1 is 1. So combined like terms, cosine and cosine is going to give us 2 cosines. So that's where this cosine squared plus 2 cosine plus 1 is coming from up here. Now I'll be able to replace either the cosine squared or the sine squared and have everything in terms of the same trig function. So I want to choose carefully here. If I replace cosine, I won't remedy my problem. Because if I replace cosine with its trig identity, I'm still going to have a cosine over here, right? So it would be better off for me to replace sine squared with its trig identity. Sine squared is 1 minus cosine squared. And I know that we've done this repeatedly over the past couple of weeks, but that identity is sine squared plus cosine squared equals 1. So if you want to know what sine squared is equal to, just subtract the cosine squared from both sides, and you'll get sine squared is 1 minus cosine squared. So we've said with those identities, you can turn them around in multiple ways. So I'm going to replace sine squared with 1 minus cosine squared. Now, everything is finally in terms of cosine, and I'll be able to solve. So let's get it all over on one side set equal to 0. So if I had a cosine squared, and I add this cosine squared over to the other side, that's going to give me 2 cosine squareds. And then if I had the 1 and I subtract that 1 over, then that 1's going to go away. Now, our whole goal here is to simplify, right? I mean, when you're solving an equation, yes, that's our objective, to solve. But when you're solving an equation, you always simplify it down as far as you possibly can and then solve, right? In 5.1, that's what the whole lesson was about how to simplify these trig functions down. And we had those steps that we used, like look for Pythagoreans and combined fractions. You can use those to help you on these as well. So if I get to a point like this and I'm not really sure what to do to simplify this down further to be able to solve it, I can go back and say, okay, step number 1, look for trig functions squared because they're Pythagoreans. Well, I don't want to undo what I just did. Step number 2, look for fractions to combine. I don't have that. Step number 3, can I factor? Well, let me see. Yeah, they both have a 2 and they both have a cosine. So absolutely, I could take out a 2 cosine. And then once it's factored, I can set each of my factors equal to 0. And then I'm comfortable from there. All right, so for this guy, we had 2 cosine x, so we set 2 cosine x equal to 0. We're going to go through and divide both sides by 2, and we'll get cosine equals 0. And then this guy, we had cosine plus 1 equals 0, so we can subtract the 1 from both sides, and we've got cosine is negative 1. So if I want to figure out where cosine is equal to 0, that's going to be at pi over 2 and 3 pi over 2. And where cosine is equal to negative 1, that's going to be at pi. Now, we have squared both sides of an equation before. It was back when we were working with rational functions. and radical functions. If you had a radical in your problem, we would try to get the radical alone. We would isolate it on one side, and then we'd square both sides to get rid of the radical. And when we did that, they cautioned us about gaining extraneous roots. And we actually had several different types of equations back first semester where we had to check our answers because we had the potential of picking up extraneous roots. If you square both sides, you are going to run the risk of extraneous roots. And here's the reason for that. When we came over here and we took cosine x plus 1 and we put a square on it, that literally means we took cosine x plus 1 and we multiplied it by a cosine x plus 1 that was not there. We multiplied both sides by a variable that was not there originally, so we've run the risk of picking up an extraneous root. Here's a simple example. Let's say that you had x is equal to 1. Obviously, that's one solution, x equals 1. But if I square both sides of that equation, that's a legal move as long as what I do to one side I do to the other side. That's okay in algebra. So I square both sides, and now when I solve that, I get two solutions. There aren't supposed to be two solutions. There's only supposed to be one. I have picked up an extraneous root, an extra root that's not supposed to be there. The only way to figure out what's the real solution and what's the extraneous solution, or if there is even a real solution, maybe they're both extraneous, is to plug them back in. So I plug back into the original equation, not the one that I had modified, but the original. And when I plug 1 in, I get 1 equals 1. Yes, that's true. But when I plug negative 1 back in, I get negative 1 equals 1. That's not true, so that's an extraneous root. So when I square both sides, I must check my answers and eliminate extraneous roots. Now, you don't have to write the checks out for me. You're welcome to do them in your head. But I wrote them out for you just so that you could see them. Let's check each one of these. The original equation was cosine x plus 1 equals sine x. So cosine x plus 1 equals sine x, where we're plugging in pi over 2. Yep, that worked. I got 1 equals 1. Cosine x plus 1 equals sine x. When I plugged in 3 pi over 2, I got 1 equals negative 1. That one doesn't work. That's an extraneous root, so I need to toss that one out. And then we plugged in pi, so cosine x plus 1 is equal to sine x. Yeah, I got 0 equals 0, so that one works. So my only true solutions are pi over 2 and pi. 3 pi over 2 is an extraneous root. All right, examples 8 and 9 are examples of multiple angle problems. It's called a multiple angle problem because you'll notice the difference right away. It doesn't just say cosine t, it's cosine 2t. It's not just tangent x, it's tangent x divided by 2, or 1/2 x. The variable that represents the angle is being multiplied by something else. So that's why it's called a multiple angle problem. We're going to start these the same way that we've been doing them, but we're going to have to do a couple things differently when we get to the end. All right, so let's start like we have been, just trying to get the trig alone on one side by itself. So I'm going to try and get cosine 2t on one side by itself. So let's add 1 and divide by 2. So we'll add 1 and divide by 2. I'm not really sure what to do with that multiple angle right now, so I'm just going to throw a theta on top of it so that I can just treat it the way I normally would. If this said cosine theta is equal to 1/2, I would know what to do. I would say, okay, where's cosine equal to 1/2? That's at pi over 3. Where's cosine positive? First and fourth. So I'd give the first quadrant pi over 3 and the fourth quadrant pi over 3. All right, two things that I need to do differently with multiple angles. The first thing that I have to do differently with this multiple angle is up here they had asked me to solve for t between 0 and 2 pi. That's usually our parameter. That's usually what they ask me for. But if you'll notice, I'm not solving for t in this problem. I'm solving for 2t. So the first thing that I have to do is, if I'm going to change from t to 2t, if I'm going to multiply the middle piece of this inequality by 2, I have to multiply this whole inequality by 2. So I'm going to go through and say 0 times 2 is 0, t times 2 is 2t, and 2 pi times 2 is 4 pi. So unlike in most of my problems where I give answers between 0 and 2 pi, in this problem I'm going to have to give answers between 0 and 4 pi. Okay, what does that mean? Well, normally when I start at 0 and I go around the unit circle, that's 2 pi. If I go around the unit circle again, that's going to be 4 pi. So the answers that I've already given are the answers for the first revolution around the circle. I need answers for the second revolution around the circle. The nice thing about that is that if cosine is equal to 1/2 right up here at pi over 3 the first time around the circle, then when I come around the circle the second time, cosine is still going to be equal to 1/2 at that exact same spot. So all I have to do is just find the coterminal. So if pi over 3 was the answer on the first revolution, add 2 pi to that, and 7 pi over 3 will be the answer on the second revolution. If 5 pi over 3 was the solution on the first revolution, add 2 pi to that to get the coterminal, and 11 pi over 3 will be the solution on the second revolution. All right, here's the second thing that we have to do differently with a multiple angle problem. At this point, I have solved for 2t. We threw a theta on top of it just so we could work with it, but it's still 2t. I've got 2t is equal to pi over 3. I'm supposed to give answers for t. So I need to go through and solve that equation. If 2t is equal to pi over 3, I want to get rid of 2 so I can multiply both sides by 1/2. The 1/2 and 2 would drop out, and I would get t is equal to pi over 6. And I could go through and repeat that with each one of these answers. If 2t equals 5 pi over 3, if 2t equals 7 pi over 3, if 2t equals 11 pi over 3. Every single time I'm just going to multiply by 1/2, right? So to shorten that process a little bit, I could just go through once I figure out, okay, I multiply by 1/2 to get rid of that 2. Just go through and multiply each of these answers by 1/2. So that would give me pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And those are my 4 final solutions. All right, let's look at another one of those. Example number 9 is also a multiple angle problem. But for this one, we've got x divided by 2. That's the same thing as like 1/2 x. All right? So I'm still going to start the same way. I'm going to start by trying to get tangent x by itself. In this case, it's tangent x over 2, but that's okay. I'm going to try and get that alone. So I need to get rid of the plus 3, and I need to get rid of the multiplying by 3. So let's subtract 3 from both sides, and let's divide both sides by 3. I'm not really sure what to do with that x over 2 right now, so I'm just going to throw a theta on top of it, and that way we can work with this like a normal problem. So we could say, okay, where's tangent equal to 1? What's my reference angle? Well, that's going to give us pi over 4. And then we can say, where's tangent negative? Tangent's negative in the second and the fourth, so we're going to give the second quadrant 3 pi over 4, and we're going to give the fourth quadrant 7 pi over 4. All right, so now we're ready for the 2 things that we do differently about a multiple angle problem. Here's the first one. Normally, I solve for x between 0 and 2 pi, but this time we were solving for x divided by 2. So if I'm going to take and divide a part of this inequality by 2, I have to divide the whole inequality by 2. So we're going to say 0 divided by 2 is 0, x divided by 2, 2 pi divided by 2 is 1 pi. So they want me to solve for x over 2 between 0 and pi. 0 and pi is just the first and the second quadrant. So when I look at the answers that I have, this one's okay because it's between 0 and pi, But this one's not. I mean, pi is 4 pi over 4. That's definitely bigger than that, 7 pi over 4. And 0 to pi is first and second quadrant. That's in the fourth quadrant. So I'm going to throw that out. So you kind of see a pattern, whereas over here, since it was a multiple of 2, I got twice as many answers. And over here, it was a multiple of 1/2, and I'm getting half as many answers. All right, second thing that we do differently is right now we have x over 2 is equal to 3 pi over 4. I don't want to know what x over 2 is equal to. I want to know what x is equal to. So I need to get rid of that dividing by 2. So to get rid of dividing by 2, I could go through and multiply both sides by 2. So I would be left with x is equal to 3 pi over 2. And so that'll be my final solution. All right, the last thing that they give us here, example number 11, is something that we did incessantly first semester with our algebraic equations, but they haven't had us do it as much with our trigonometric equations, and they don't want us to lose those calculator skills that we built first semester. So example number 11, they ask us to use our calculator to determine where x is equal to 2 sine x. All right, a couple of different ways that we did this first semester. Probably our favorite way, or the most popular way that we did this, was we would take what's in the left-hand side of the equation and put it in y1, and take what's in the right-hand side of the equation and put it in y2, and graph it. When you graph it, what are you looking for? Where are they equal to each other? Where they intersect, right? So all I'm going to do is hit my intersect button, and that again is second trace, which is my calculate menu. I can go down to intersect, and it'll ask me for, do you want me to use this for the first curve? Enter for yes. Do you want me to use this for the second curve? Enter for yes. What's your guess? And then it will tell me that point of intersection. The other way that we did this, probably not as popular, but still a possibility. The other way we did this was we moved the entire function over to one side so that it was set equal to 0. So I could subtract this 2 sine x over to the other side, and it would be x minus 2 sine x. If I put that into y1, that's where it's set equal to 0. So what am I looking for on the graph? X-intercept, right. Solution, 0, root, x-intercept, all synonymous terms. So again, if you go to second trace, which is your calculate menu, and go down to number 2, then you can find your root, your 0, your x-intercept, your solution. It's going to ask you for a left boundary, a right boundary, and a guess, and then it'll tell you that x-intercept. So it doesn't matter which way you do it, you're going to get the same answer for x, which is what we were trying to find here. So good review for us. All right, so here is our homework for tonight. We're working on pages 400 to 401, pages 400 to 401. Just a couple of these tonight will definitely cover it. 17, 32, 33, 35, 43, challenge 93.